Hello and welcome to Lecture 2 of the Forces unit in Phys 1104. The main goal of this lecture is to learn to draw good free body diagrams, which is a key skill for the rest of this course and probably for many other courses that you'll take in the future. The vector sum of forces is the rate of change of momentum, and there are two ways for momentum to change. Either the velocity of something could change, or the inertia of something could change. We're going to focus on velocities of things changing. We're not going to look much at inertias changing, but that does happen, for example, in nuclear reactions, or if you're thinking about a rocket and not including the escaping gases in your system, then you have a system which has a reducing inertia. But we're going to focus on changing velocities, and in that case, then, the vector sum of forces is directly related to the rate of change of velocity. And we know what that is. That's the acceleration. So think of Unit 3 of the course, which was all about acceleration. And there we saw that if we know the initial position and initial velocity, we can use the acceleration to solve for everything that the object does after that. And so knowing all the forces and knowing the initial position and velocity of an object gives us enough information to predict everything about the future motion of that object. I want to take what I've just said and put it in the simplest possible terms because it's very important. So the answer to this question of what do forces do is that they cause objects to accelerate. Now, I'll caution you that isn't the whole answer, but it is the most important part of the answer. But even so, there are subtleties even to this simple part of the answer. Let's think about a car going around a corner, and let's say we've made detailed measurements on its velocity, and we know which way the acceleration is at this instant from analyzing the motion. Then we can conclude that the vector sum of forces points in the same direction as the acceleration, because the acceleration is always in the direction of the vector sum of forces. But remember, it isn't the acceleration that's causing the forces. It's the forces that are causing the acceleration. Very important. Forces cause accelerations. Accelerations do not cause forces. What causes forces is interactions with objects. A useful piece of terminology is translational equilibrium. An object at rest is in translational equilibrium, but another possibility is an object that's moving at constant velocity. Equilibrium means no change, or things being in balance. And so an object in translational equilibrium is an object in unchanging translational motion, or in other words, constant velocity, and zero counts as constant. So we've seen that when the vector sum of forces on an object is zero, the object moves with constant velocity, or in other words, it's in translational equilibrium. But we've already seen this idea much earlier in the course in another disguise. Think of the law of inertia. As viewed from any inertial reference frame, any isolated object moves at constant velocity. Well, an isolated object is an object that isn't interacting with the environment, except we now see another possibility. If all the interactions cancel each other out, that's the same thing as not interacting with the environment. And so having a vector sum of forces that is zero acting on an object is the same thing. That's isolated. And constant velocity is the same thing as translational equilibrium. So in other words, these two laws here are just equivalent statements. They're two ways to understand the same law. One reason to understand translational equilibrium is to avoid being fooled in situations where objects aren't accelerating, even though there are many forces acting on them. And so it's good to look at what else forces can do to objects. We already know that forces can cause objects to change their velocity, or in other words, accelerate. And so that's a change in the translational motion of the object. But even when the vector sum of forces is zero, if the forces aren't lined up with each other, they can cause the object to accelerate angularly, or in other words, to change its rotational motion. Also, forces can cause objects to be deformed, which is a change in shape. So we're largely going to be concerned with how forces cause things to accelerate. We've already seen, though, changes of state like deformation and other changes of state such as warming up due to frictional forces, and we'll continue to look at that. What we unfortunately won't have time to look at, because it's very complicated, is rotational motion. To give you practice thinking about forces and motions of objects, let's think about an air puck. So suppose we have an air puck that's just hovering, stationary. Because it's stationary and staying that way, we know that the acceleration is 0. Now, you can verify by picking up the air puck and dropping it, which you shouldn't do, you'll probably break the air puck, that it will accelerate down if you do so. And so we know that there must be a gravitational force acting on the puck. The Earth is what's exerting that force. But when it just sits stationary and hovering, we know that that can't be the only force because we know the acceleration is 0. So there must be an upward force, and it's not so obvious what causes it because what causes it is invisible. It's the air. The puck pulls air in at the top and pushes it out at the bottom, and through that interaction the air pushes up on the puck, and that's what lets it hover. And so we know that the vector sum of forces between those two forces is 0 because the acceleration is 0. But now suppose the air puck isn't stationary. Suppose I take the air puck and I give it a little shove. Then what we find if we look at it is that after it leaves my hand, it moves at a constant velocity. Let's actually see that. So here we see the puck, and you can see the motion diagram track being produced there, and that is clearly constant velocity motion. I'll put in the whole motion diagram and I will zoom in, and it becomes even clearer that this is constant velocity motion. This situation of the air puck is perfect for you to check your understanding of some of the ideas that I've just been talking about. So here's this situation. I've just given the air puck a push, and now I'm not pushing anymore, and we find that the air puck is moving along to the right at a constant velocity, and I'm going to specify that air drag here is negligible. And so which of these diagrams shows the best representation of the forces acting on this air puck?